today's video is going to go over how to evaluate a limit analytically. And I'm starting a little down into the notes, so if you've printed these from It's Learning, I'm starting with this question here. When a function is defined and continuous at a value x equals a, how can the limit as x approaches a of f of x be found analytically? So basically we're saying if the function is defined everywhere and you can trace the graph and go through a point without lifting your pencil, how can you find the limit? And the answer to that is through direct substitution. Because basically what's going to happen is when I trace the graph to find the y value, that's going to be the same as plugging the x in to find the y value and evaluating the function value there. So for letter A, the limit as x goes to 3, we are dealing with a function that's a quadratic, and this quadratic opens up. So this is a parabola that's smoothly connected everywhere, and when I plug in 3, whatever I get for the y value, that will be the limit. So we're just going to plug in 3 for every x, and then do some mental math because you're not using your calculators, and we will have the answer to our limit. So this will be 9 halves minus 6 plus 3, and when you do that math, you should get 3 halves. Okay, same thing for B. If we want to evaluate the limit, we're just going to plug straight in. So the limit will be 5 times 3 plus 2 over 2 times 3 minus 3. So that gives us 17 over 3. All right, so we're going to continue this process. Even in part C, it's approaching 2 from the left. Just because it's approaching 2 from the left doesn't mean you don't plug in 2. So you're still going to directly plug in 2 and get your limit. Same thing happens with part D. This is a trig function, but we're still going to plug in 4 theta pi over 2. The only trick here is that you've got to remember your unit circle. So we're going to multiply 2 times pi over 2 first. So we're actually evaluating sine of pi. And then you've got to remember your unit circle. Pi is the same thing as 180 degrees. The sine value is the y-coordinate there. So for this limit, our answer would be 0. And so we're just going to continue doing this for all of these problems. I'm not going to work through all of them, but you're going to basically replace your variable with whatever you're approaching and then simplify. So plug it straight into your equation, your function, and then simplify. So again, on E, you'll have to use the unit circle. And then for part F, you're going to need to know a little bit about logs. Okay, so direct substitution, that's our process. But what happens if we directly substitute and we get some issues, or we have some issues, and things don't work out necessarily the way we would like to? So let's plug in right here. We're going to plug in -3 and see what happens. So as I clean this up, I'm going to say, okay, well, -3 squared is 9, minus 12, that's -3 plus 3, I get 0 in the numerator. Okay, not so bad. We can't have 0 in the numerator of a fraction. But then as I clean up the bottom, I have 9, minus 6, which is 3, minus 3, which is also 0. Oh, wow, you cannot have 0 in the bottom. So does the limit not exist? Well, not necessarily. Let's just hold on to that thought. Direct substitution here produced 0 over 0, which is what we call an indeterminate form. But it doesn't necessarily mean the limit doesn't exist. So hold on to that thought. Let's try this one. These are the same function, this, the second one and the third one, and we're plugging in 1. Even though it's from the left, we're going to still plug in 1. So it'll be 1 squared plus 4 times 1 plus 3. And then 1 squared plus 2 times 1 minus 3. For this problem, we're going to get 8 in the numerator, and oh man, in the denominator we're going to 0, and that's a bad thing. Over here, since it's the same function and we're still plugging in 1, we're going to get the same outcome. So all 3 of these produce a 0 in the denominator. However, Just because a function is undefined at a value of x does not mean that a conclusion cannot be reached about the limit. So let's look at this function again, but let's look at the graph of this function and see if we can evaluate these limits this way. As I'm approaching -3, I'm going to trace the graph from the left, and then I'm going to trace my graph coming in at the right. And it does appear that a limit exists. As I approach -3 from both sides, I'm trying to reach that hole, and the coordinates of that hole are up here. So it looks like I'm trying to reach a y value of 1/2. So I would say this limit is 1/2. But oh wait, when we tried direct substitution, we got 0/0. So what's going on? We've got to be able to solve these algebraically. We can't just stop when we get 0/0. So we're going to examine the other limits at 1 from the left and right, and then we're going to talk about what can we do in this situation when we get 0 in the bottom. So as I approach 1 from the left, it looks like I'm going to -infinity, which is more descriptive than 8/0. And as we evaluate the next one, 1 from the right, I'm going to approach 1 from the right, and it appears, approaching 1 from the right, that I'm going to +infinity. Again, that's a better description than 8/0 and say an undefined. So we've got to be able to solve all three of these limits, but using algebra. So let's take a look at this. How did we, in pre-calculus, determine where holes and asymptotes were? Basically, we found these discontinuities, such as holes and asymptotes, in pre-calculus by factoring. If we factored the function, then we were able to identify holes and asymptotes. So we're going to have to do this same thing, this same process. We call this the cancellation process, where we are going to factor and clean things up so that we can identify these holes and these asymptotes in our algebra, and then that will help us determine the limit. So this is going back to the same one that we got 1/2 up above. Let's take a minute and let's factor the numerator. So we need two numbers that multiply to give us 3 and add to give us 4. That would be x plus 1 and x plus 3.
Attention teachers.
Okay, oops, sorry about that interruption. And now we're going to factor the denominator, which will become x plus 3, x minus 1. In this case, now we're able to cancel the factors of x plus 3. And you may recall from pre-calculus, remember when factors cancel, that's what produces the hole in the graph. But we've also learned that just because there's a hole in the graph doesn't mean the limit doesn't exist. It actually does. So what we can do now is now we're able to go back and directly substitute. So we've got the limit as x is approaching -3, x plus 1 over x minus 1, and we're going to take -3 and directly substitute. So in the numerator, I'm going to get -3 plus 1, which is -2. Denominator -3 minus 1, -4, and that reduces to 1/2. So now I'm able to see that the limit's 1/2. So the trick here is always try direct substitution first, but just because you get a 0 in the denominator doesn't mean you stop. You should at that point try to factor, try to simplify your equation, your function, and then directly substitute again. Okay, let's see what happens with the ones where we were at 1. Basically what we need to remember here, apologize, I'm going too fast. Based on our knowledge from pre-calculus, we know that if a rational function has a non-removable infinite discontinuity, graphically a vertical asymptote exists. So that non-removable infinite discontinuity is the same thing as a vertical asymptote. That's just a new fancy vocabulary word for you. Since the y values do not approach any specific value from both sides at a vertical asymptote, then a limit does not. I'm sorry for the interruption again. One of these days I'll learn not to record a video during the lunch period. Okay, so even though the limit will not exist at 1, because these are one-sided limits, we should decide which direction the graph is going, because that gives us a little more description about the behavior. So we have factored this equation already. We know that when we plug in 1, we get a 0 in the denominator, so we factored. And when we factor, we get x plus 1 over x minus 1. You can go back and look at the factoring we just completed a minute ago. This is the same function. But when I plug 1 in, I still have 0 in the bottom. So we have to know that at x equals 1, there's a vertical asymptote. So the limit doesn't exist. But since I'm approaching 1 from the left, I'm actually going to test a value so that I can give a more descriptive answer. So a number that's immediately to the left of 1 would be 0.9. I'm going to plug 0.9 into my factored form. And I really don't care what this number is. I just care as to whether it's positive or negative. 0.9 plus 1 is positive, and 0.9 minus 1 will produce a negative. So my overall result is negative. Since my overall result is negative, I will say this limit is negative infinity. And that will confirm what we got graphically a minute ago. We're going to do the same thing with this one. We're going to plug in 1, realize it has a 0 in the denominator, so we're going to factor. But then when we try to directly substitute, it still doesn't work. So we're going to pick a number just to the right of 1, 1.1. And we're going to plug it into our equation. 1.1 plus 1 is positive. 1.1 minus 1 is also positive. So that's a positive overall. Therefore, our limit is positive infinity. So for both of these examples here, for the one from the left and right, the limit as x approaches 1 of f of x still does not exist. But because these limits are one-sided, we want to give a more descriptive answer, so that's when we test values. Okay, so there you go. That's how you evaluate limits analytically. You directly substitute the value of x into your function. If it doesn't work, you get 0 in the denominator. Then you should try to factor and clean up and then try direct substitution again. If direct substitution still doesn't work and you still have 0 in the denominator, then you most likely, you have a vertical asymptote in your graph and your limit will not exist. Okay, stay tuned and watch video part 2 if you want to see a few more examples.